Alright guys, back finishing up the vodcast to lab 3.1p. We're on part 4. What does the boiling point of each liquid tell you about the strength of the intermolecular interactions? This is a very common question, and what I just want you thinking about is this. Increasing boiling point equals increasing strength of intermolecular interactions. Okay? So the higher the boiling point, the larger the strength of the intermolecular interactions. We can think of the intermolecular interactions if we had two molecules. That little friendship between them, that's the inter connection, and the within connection, that's the intra. So the stronger the inter, the harder it is to separate these two from one another, and the harder it is thus to boil it. So based on your answer, rank each molecule in order of increasing inter, and intra. So let's look at our chart. Okay. According to our chart, the highest was oil, second was water, and the third was alcohol. So let's rank it. And this is just simply based on our answer to the above question. So according to the above question, ethanol would be last, then water, and then oil. So now here's where it gets interesting. Does your answer agree with your answer in part 1 or part 2? If not, explain the discrepancy. No. In part 4, oil has the highest intermolecular attraction, and in parts 1 and 2 it has the lowest. Very interesting, okay? That we just answered the question. Okay, now in 4 it says the strength of intermolecular attractions is highly related to the type of intramolecular attraction. So basically it goes on here to talk about the hydrogen bond, and that hydrogen bond is when hydrogen is covalently attached to either oxygen, nitrogen, or fluorine. This is our NOF that we talked about earlier. Hydrogen has to be connected to N, O, or F. So it says, use the concept of hydrogen bonding to explain why water has a higher boiling point than ethanol. So if you look at the Lewis structure of water, and you look at the Lewis structure for ethanol, I'm going to label the hydrogen bonds here in red. This has 2 hydrogen bonds, and this one only has 1. So we can simply say that water has more hydrogen bonds than ethanol. Thus has a higher boiling point. All right. So although it has no hydrogen bonds, and let's take a quick look back at it to make sure. If you look at, do it in blue, you look at all the hydrogens are connected to carbons in this molecule. All the hydrogens are connected to carbon, and that is not a hydrogen bond because hydrogen has to be connected to N, O, or F for it to be hydrogen bond. So let's go down here, and it says, although it has no hydrogen bonds, oil does have a higher boiling point than water and ethanol. And I basically ask you to work with each other to figure out why this rule is violated, and I ask you to think about the molar mass, which is a large hint. So, 99% of the time, the substance with more hydrogen bonding is going to have a higher boiling point. Whereas in this case, you have H2O, 100 degrees Celsius, you have ethanol, 80 degrees Celsius, and you have oil, which was 140 degrees Celsius. So there's a huge discrepancy. 2 H bonds, 1 H bond, 0 H bonds. We would really predict water to have the highest. This trend is really going down, down, and then it shoots up. And we want to know why it does that. Well, in this case, a good hypothesis would be that although oil has no hydrogen bonds, it is a very large molecule. Okay, we're talking C10H20. The heavy nature of this molecule increases its boiling point and affects its ability to become a gas. So basically what I'm saying is that although there are no hydrogen bonds, because oil is so large, is such a large molecule, and let's go up here above this and write it in. We got H2O, we got C2H6O, and then we have C10H20. Because it's such a large molecule, it's going to have a high boiling point. Notice the rest of the tests lost. For instance, the vortex time was very low. In the density column, it was not as tightly packed as water. It could float on top of water. And in the penny drop, you could really fit the least amount of pennies, least amount of drops of alcohol on the penny. But in the boiling point situation, it did win. It's so heavy, it does not want to become a gas. But, you know, really, if this was not C10H20, if this was CH4, and we know that CH4 is methane, it's a gas at room temperature. So the carbon-hydrogen bond does not create stronger intermolecular interactions than the hydrogen-oxygen, hydrogen-nitrogen, or hydrogen-fluoride bond. But in this case, there were so many carbons and so many hydrogens that it did cause an increase in boiling point, not necessarily an increase in the intermolecular interactions, just simply an increase in the boiling point. The other tests did show that water does have the highest intermolecular interactions. So if we want to look at this one more time and just think about it, the graph would be a good place to begin. When we look at these molecules, first we know that they're all covalent. There's no metals. In terms of the vortex time, water held the vortex the longest. That definitely shows that it's got the strongest intermolecular interaction. Okay, it held that vortex time the longest, meaning that the water molecules were very friendly with each other. They wanted to hang on to their position. We also saw that water held the most drops of water on the penny, showing that water really is friendly with itself. It's a very sticky molecule, therefore it hung on there on the penny much longer than the ethanol or the water, demonstrating that it does have stronger intermolecular interactions. We also saw that water was at the bottom in our density column, once again showing that water is very tightly packed. It's got very strong intermolecular interactions, very friendly with itself. And in the boiling point, though, we did see oil win, and we said that this was due to weight. All right, so even though it's heavier, it does have a higher boiling point, it does not have stronger intermolecular interactions. Take care, everybody.